Hey, pre-calc students, this is going to be another lesson in our functions unit. Today we're going to talk about two different things. One is this concept called reverse composition, and we're going to see how we can build off of our knowledge of composition of functions here. We are taking notes by hand if you haven't guessed already. So if you want to take out some paper to get yourself started here, you can do that. The other thing we're going to talk about today is something called the difference quotient. And difference quotient is actually super important and critical in the study of calculus much later on. So we'll definitely come back to this concept of the difference quotient later on in the year. But to get started with the reverse composition, what we have is in these examples, these functions defined by h of x. You'll see everything down here says h of x, h of x, h of x, h of x. And h of x is already a composition of two functions, f of x and g of x. So what we kind of want to do is we know how to, if given two functions, we know how to kind of put them all together, compose them into a single function. What I kind of want to do with these is break them apart. Which two functions, when composed together through this composition process, could go backwards and get us the function h of x there. So when you have this function f of g of x, I almost want you to think of f as being, what's the big idea? Like, what's the parent function that's going on? And if you think of that being the parent function, we can then think of g of x as what am I plugging into the parent function to make this new function h of x. So let's see if we can use that logic in a few of these examples here. Number one, h of x equals x plus 1 squared. I'm hoping the parent function that jumps out to you right away is x squared, right? This is some sort of squaring function that's happening here. So if we were to break this down into f of x and g of x, f of x I'm just going to call the function x squared as the parent. And then for the function g of x, what got plugged into this x quantity and then eventually is squared? It's what's on the inside of that parentheses. It's the quantity x plus 1. And what you should be able to do right now is do the composition f of g of x and get back to the original example of what we have written in h of x. And hopefully that would make sense, right? F of g of x would say take x plus 1, plug it in for x here, and that's going to get us back to x plus 1 squared. So that's the whole idea of reverse composition, and I know you'll see examples like this come up in the textbook for homework. Moving on to number two, h of x is equal to the absolute value of x minus 3. So what are the two functions that would be composed to get this as my total function, h of x? Well, if we think about the parent function in this case is we're dealing with something with absolute value of x. And then for g of x, what got plugged into the absolute value function? It's the inside quantity here of x minus 3. And if you were to do the composition, f of g of x, yep, I'd take x minus 3, plug it in for x right there, and we get back to the original function h of x. What I'm going to make a quick note about here is that there's not necessarily a unique answer, okay? So if you are trying these and you see my answers and they don't quite match, that's okay, because you can define these functions in slightly different ways and still get a composition that gets you back to h of x. So even though, in my opinion, there might be a more obvious way to go about it, like this seems pretty direct based on how I've broken down the first two examples. If you think of it in a different way, but your composition still gets you this function h of x, then you're definitely on the right track with that. Taking a look at these examples here in number 3, the parent functions start to get a little bit more complicated, I guess, here, maybe even some parent functions that we're not super familiar with, but we can still break this down into terms of f of x and then a function g of x that would produce the composed function up here, h of x. So I think whenever you see a parentheses, what I would consider doing in this example and for all future examples is think of the parent function as just some single x value in each of those locations. So for example, if you let the function f of x equal x squared plus x and then minus 4, hopefully it would make sense to you to define g of x to be x plus 7. Because then what would happen is I would come up here and I'd replace both of those x's with the quantity x plus 7. And that would match the original h of x function through that composition. We do want to include the -4 there, right, in the function f of x for the parent function, I've called it. Just double check that if you're missing something, you don't want the -4 down here because then it's going to get plugged in for those x's as well. Double check that composition in your head and see if it makes sense. Similarly for number 4, you might want to define f of x. Wherever you see that quantity in parentheses, replace that with an x. So we'll make this x squared over x minus 3. So therefore, what would g of x need to be such that when I take the g of x function and I plug it in for those two x's, we get back to the original. Hopefully you're seeing clearly here that g of x should be then x plus 4. And this whole idea of reversing a composition is also actually a good skill in calculus. There are times where you're trying to do something where you're applying calculus to a function that looks like this. And it's nice to be able to break it down into two pieces that might be a little bit simpler, such that we can then apply some calculus techniques. So that's the whole idea of pre-calc, right? I mean, taking things that we're going to eventually use in calculus, but learning some of the techniques that might be involved to algebraically, in this case, break something down into simpler parts. So with that being said, why don't you, before I see you next, try these two examples quick. So you're going to try number 5 and number 6 in your notes. Okay, reverse the composition there, come up with an f of x and a g of x that represents these two functions, h of x in each of these cases, and we'll go over those next time I see you. So beyond reverse composition, we also have something, like I mentioned, called the difference quotient that we're going to look at. So the difference quotient, like I mentioned at the beginning of the lesson, it's a huge, 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 huge concept in the study of calculus. And essentially what it boils down to, without applying a calculus concept to it yet, is just evaluating with functions. So when I say to do f of x plus h, it means take a function f of x, and every time you see the quantity x, we're going to replace it with x plus h. Then I'm going to subtract the function f of x from that, all in the numerator, and then divide by h. So this is just kind of some quick practice here to get used to what this whole difference quotient evaluating looks like. And I'll tell you some common patterns and trends that we should be looking for as we simplify here. So for number 1, f of x equals 2x plus 1. If we apply the difference quotient, the first step of f of x plus h should look like this. 2 times x plus h, and then plus 1. So it's taking the function f of x. Everywhere I see x, we replace it with x plus h. Don't forget that that plus 1 would carry down as well. Then from that, you need to subtract the function f of x. Whenever I do that step, make sure you subtract it by putting the whole thing in parentheses and then divide everything by h there. Okay. So then from there, we're just going to do some algebraic simplifying. We got to clean up what's in the numerator there and see what we have left over in the end. So I'm going to distribute the 2 here, and then I'm going to distribute the negative over here. So we get 2x plus 2h plus 1. Distribute the negative, minus 2x minus 1, all over h. From there, you'll notice that some key things cancel out in the numerator. We get 2x and negative 2x to go away. We get positive 1 and negative 1 to go away. So the only thing that we're actually left with on the top is 2h, and then on the bottom we have h. And very clearly, hopefully to you in this case, those h's would then cancel out to get that the difference quotient for the function 2x plus 1 is actually just equal to 2. Now, one hint that maybe isn't as apparent in this one, but will become very apparent in future examples, is that you're on the right track if when you do that canceling on top, that canceling step, everything that's left over has an h in it. That's going to be something I really ask you to pay attention to. Here we only had one term left on top and it happened to have h, so that was good news. But I'll tell you, there will never be an h left in the denominator. That h that's in the denominator will always cancel with h's that are in the numerator. Let me show you what this looks like for maybe a quadratic function x squared, because it's going to start to look a little bit different here. So for the second example, when we apply the difference quotient, we're going to say that we're going to get the quantity x plus h squared. All right, that would be f of x plus h, minus f of x, which is just x squared. I don't think you really need parentheses around it, right? It's just a monomial. If you had a binomial like we had over here, you definitely want to distribute that negative across. And then all over here, you're going to put that all over h. So that's your first step. Okay. Here's what students classically do wrong all the time when they square a binomial. They just distribute the square and call that x squared plus h squared, which is very untrue. Okay, I'm going to do this once super fast. If you're going to do x plus h times x plus h, you might want to do box method because you will get x squared. You will get h squared. But you're going to get these two terms that are xh, xh. So if you add up those two xh terms, the middle term of the trinomial that you'll get is 2xh. So what I'm going to write in the next line is we definitely get x squared, but then plus 2xh is very commonly missing from student work at times. And then plus h squared minus the x squared all over h. Okay, so I think that hopefully you can start even thinking of this without doing the box method off to the side. But if you are, want to avoid making mistakes, show that little box method, do some FOIL. We got to get that trinomial correct there. Okay, x squareds cancel out. So I want you to look at what's left on top and then think what I just mentioned a second ago. Does everything on top still have an h in it? And the answer to that is yes. So we know we're on the right track if that's true. What we're going to wind up doing is take out h as a GCF. And when I do that, you're left with 2x from the first term plus then h from the second. And then here those h's cancel. To get your final answer, the difference quotient for x squared is 2x plus h. So as compared to the first one, the difference quotient does not have to end in just a single numerical value. Your final answer can have x's and h's both in it. And that gets a little weird sometimes for students, but the answer is not necessarily a number in the end. It could be an expression that has both x and also h in it, like we see in this example here. Let's try this process one more time for maybe a slightly more complicated looking quadratic. So we'll do number 3, and then I'll give you one to try on your own as you think about finishing up some practice in the notes here. Okay, so for number 3, the difference quotient, f of x plus h, what that would look like to start is you would do 3 times x plus h squared minus the quantity x plus h plus 2. That's just the step for f of x plus h. I replace both those x's with the quantity x plus h. From that, we're going to subtract f of x. Okay, and then that all goes over h. Okay, now remember, x plus h squared we just did a second ago in the last question. X plus h squared, if I come up here, was all of this, right? X squared plus 2xh plus h squared. I'm going to kind of cheat a little bit and not write that out in the next step. I'm going to write that out, but I'm going to also distribute the 3 at the same time. Sorry if that's a lot of work at once, but I already know that this is x squared plus 2xh plus h squared. I already know that. So why don't I just distribute the 3 into that so I can just kind of save myself a little bit of room for the work I have to show. So that's going to be 3x squared plus 6xh plus 3h squared. Okay, make sure you do square it before you triple it, right? That's important for PEMDAS. But other than that, I'm okay if you kind of jump to this step here. Distribute the negative to get minus x minus h with that plus 2. So now all of this expanded is now written in the next line. At the end, when we subtract f of x, distribute the negative to all 3 of those to get minus 3x squared plus x and a minus 2 all over h. Don't forget about that all over h step. That's kind of important. All right, so keep going. Now we get to do the fun step, in my opinion at least. Who doesn't love crossing off terms, right? 3x squared and negative 3x squared go away. Negative x, positive 2, negative 2. All of that cancels out. And how do I know if I'm on the right track? Well, we know we're on the right track if everything left has an h in it, and it certainly does. We have 3 terms in the numerator, 1, 2, 3, all of which have h. So I'm okay if at this stage you take out an h as a GCF, so that leaves me with 6x plus 3 Now you just have one h there. And when you take h from h, you have to put -1 at the end. That's kind of an important step. Okay, all over h. And if you took out that GCF correctly, you're essentially done, aren't you? Because those h's cancel, and your final answer is 6x plus 3h minus 1. So that would be what the difference quotient looks like for the function 3x squared minus x plus 2. So, definitely make sure you're giving yourself enough space when you expand all that stuff going on in the numerator there. But once you've done that step, a lot of stuff will cancel out. And like I said, you know you're on the right track if everything left has an h. So what's the challenger that I'm going to give you to try? The challenger that I have for you is this one down here. Try. What if we had f of x equals x cubed minus or x cubed plus 1? Do the difference quotient evaluation for this and see what you get in the end. X to the third plus 1. I'm going to give you a little bit of a hint because at some point in this process you're going to get x plus h cubed, right? So how do I cube a binomial? You can't just distribute the cube into both. That's the classic mistake that students make sometimes when it's squared. You already know, though, what x plus h squared looks like, don't you? So if you know what that is from the last two examples we just did, multiply that by one more x plus h, and then that is what x plus h cubed is. So it kind of gets you to that next stage where maybe I don't have to do like box method a couple times, maybe just once, because we already know what this stage looks like. Multiply it by one more, and that's what x plus h cubed is. So there's my hint. I hope that you use it because I think it will help. And if you have any questions about this at all, we will talk about it next time I see you. Have a good day.